And so they come in all different sizes and packages in different ways. These stud-mounted diodes, let me bring my camera up. I thought I did. Which you got a little small one there. So what basically determines the size? The amount of current they can cut. Now we could look these up. Oh, I can go to a web page. Category. This is a shunt I'll pass it around. So normally I've got a ammeter up on my operator's control panel. I don't want to bring 500 amps to my panel. So what we do is we do very similar to what your amp meter does, is we put a shunt out there. So my meter would attach right here, and all I'm doing is measuring voltage. This is a 50 amp, 50 millivolt shunt. So that means at 50 amps, it draws 50 millivolts. So that's basically 1 millivolt per amp. So now I can have a 50 milliamp movement, right? You understand, meter movement. So it's full scale when it sees 50 millivolts. When it's full scale, it sees 50 millivolts, and I just put amps up there. So instead of putting volts, I put what on my meter? Amps. So if it's showing me, 20 millivolts, it would be it would actually be 20 amps flowing through the shunt, right? Does that make sense? So this is a true shunt. But 50 amps, 50 millivolts, very precise. These things are very precise in their resistance. What would that resistance be? We probably couldn't measure this resistance with a regular meter, with a regular 3.5 digit meter. It measures 0 ohms. So this is basically what it does. Now, the lower the current that it's designed to measure, the more resistance it's got to handle, right? You understand? So if I've got a 50 millivolt movement, then I have to make it drop 50 millivolts, even though I'm only got 50 milliamps. So it might have 100 ohms. And you can measure the shunt in your meter. Just take another ohm meter and put it on ohms and put it across your high current, the common in your 20 amp range, and you're measuring the shunt. And then you can put it between that and your milliamp range, and you can measure the shunt. The milliamp range is probably going to be in the range of around 100 ohms. But it only has the ability to measure 40 milliamps. So it's not going to drop enough voltage, to cause you any problems anyway. So here's a shunt. These are diodes. And by the way, these are stud mounted. This is what we call a pigtail, by the way. This is very nice because it's really flexible. So this allows whatever the diode's on to vibrate and not have a mechanical connection. And also it helps us with alignment. But what you got to understand is just because you have a stud, it does not mean it's the anode or the cathode. It's going to be one of them, but you don't know. So I'm looking for my symbol on this one, if it's still on there. So this one, here's the diode symbol, and the cathode is pointing toward this guy, right? And then I come up and get another one. Y'all probably can't see this one because it's pretty dark. The cathode is pointing toward the pigtail. So it makes it a little different. So you just can't go out and say, well, we need another diode, and you find one that looks like the other one. You need to make sure it's what. Can I check this with an ohm meter? It's a diode. It's made out of silicone, guys. Can I check it? Sure. It's just that they're going to be heavily doped, and sometimes we get them confused with germaniums, because germaniums drops around 300 millivolts. But these guys are going to be around 400 millivolts, and they're silicone. They're just heavily doped so they can handle a lot of current. And if you don't know what the anode is, if the symbol's wore off, then what can you do? You gotta take your meter, get it out, take your meter, if I can get it so we can see the scale. There we go. And I'll just come over here and I just touch this side and that side. It gives me no reading, so I probably got it what? Reverse biased, right? I come up here and swap it around, put it over here, and there it is, 400 millivolts. Is it good or bad? It's good. Now, if I had a resistance reading backwards, it means the diode is if the diode is leaky. If I come over here and measure ohms, you might as well throw that sucker away. Right? You understand? Or if I come over here and it measures 1, 3, 4 volts to break it down, you might as well do what? Throw it away. If it measures open in both directions, it might not be a diode. It might be something like this. Look at this package right here. I've seen diodes in this package right here. We call these hockey pucks. Looks like a bomb, yeah. This one I think was rated at about 600 amps. This one we can't check with an ohm meter because it's not a true diode. It's a device called an SCR, and that's what this little conduction little thing is right here. They have diodes in this same package, and you have to clamp them into a unit. And usually it's got to be heat sinks or water cooled. Most of these things run in, well, I should have brought the other one over here. Usually we run it to water cooled because the heat sink on these would be so big that they would be used. So what we do is we just clamp them in a water cooled jacket, kind of like some other devices use, right? So want to see these? Don't come get some. So those are just diodes, guys. That's all they are, and we can check them with an ohm meter, no matter how big they are, right? Even that big old SCR, we could probably figure out how to check it. We'll talk. That's one of the devices we'll talk about. So any questions so far? Now, one of the main uses of a diode is to do something called rectification. In fact, they call the 1 in 40,000 series, they called it a rectifier diode. It is designed to rectify. So what do we mean by that? Well, what would happen if I come over here? Of course, we're going to have to protect this thing as a resistor, because if I forward bias this thing in a power circuit and I don't protect it with a resistor, it's going to act like a closed switch and it creates a short circuit and it's lost. It's gone, right? I'm going to come over and put a resistor right there. And then I'm going to come over and put my diode. Let's swap it around. We'll put the diode first. In fact, I'm going to insert just a blank slide so I'm not drawing around. So I'm going to come over here, and so we have this symbol right here. And what's this a symbol for? What's that a symbol for? It's for a DC voltage source. Now, this is the first symbol we adopted for batteries. But this is the symbol for a DC. This would be the symbol for this thing. Is this a battery? This is a electronic device that converts AC to DC. The only thing we would add would be this right here. So anytime we see that arrow drawn through a device, it means it's variable. So that's a variable DC voltage source. But we still give it the symbol of a battery. So it originally was a symbol for a battery, but it is the symbol for any DC source, whether it's electronic or whatever, right? You understand that? Then we got this symbol right here. We draw a circle, and then we put this little squiggly line in it. This is a symbol for an AC voltage source. Of course, we can't have current unless we have what? Voltage. We have to have a difference in pressure. So this is a symbol for an AC voltage. So what I'm going to do is I'm going to come over and take this symbol, right, and then I'm going to come up and I'm going to hook it up to a diode. And then I'm going to hook it up to a load. By the way, what's this a symbol for? Huh? Symbol for common. See, and this is probably one of the most misused symbols in electronics. That's a symbol for ground. But we do have some electronic circuits that are not connected to ground, right? What is ground? Earth ground. So I mean, somewhere to legally use that symbol, we're supposed to have a nice copper rod. It used to be solid copper, but they don't do it anymore because the inside of the copper is not exposed to earth ground anyway. So just about all your ground rods are usually a metal like aluminum or something, and they're copper plated. And then they drive that thing in. They have to be about 6 foot, and then they drive it down into earth ground, and then they hook a wire up to it, and that's ground. That's a true ground. But just about everybody uses this guy, and they call it ground. Even you probably heard your automobile. They talk about the black lead. They say it's ground, but it's not. It's common, right? You understand? So you need to understand the difference whether they use the wrong symbol or not. So my cell phone doesn't have a ground. If it did, they would have a what? A wire would be running out of it. It'd be attached to a copper rod going down, or a copper pipe. Copper pipes make really good grounds too. If the water company runs copper pipes, if whoever wires from your meter, if they use PVC pipes and then they connect it to copper pipes under your house, then that's not a good ground, right? You understand? So to get a good ground, it has to run. You need to have copper pipes running from your meter into your house. If not, then you just to do what? To get a good ground, you need to have a ground rod out there. So my house is like that. It's got PVC running from my water meter up to my house, and all the piping in my house is copper. So what do I have to have? I got to have a ground rod. So what's going to happen here, guys? Well, this guy puts out a voltage that looks like this, and so we're going to have to learn this. So we called it an alternation. It goes up at a slope. It hits a peak. It comes back down. This is the way AC power is generated. Right here, this is 0 volts. Then it changes polarity, and this is the mirror image of this guy. So during this time, the diode would be off, right? Because it's not forward biased, it's not reverse biased, it is not biased. It has no negative voltage or positive voltage. That makes sense? And then the guy starts up. Is the diode forward biased? No, because it's got to exceed the barrier voltage before we say it's forward biased, because when it's forward biased, it's supposed to conduct. But when this thing gets about 0.7 of a volt, then this is going to be positive, right? You understand? Definitely positive. What's this going to be right here? Well, no, it's going to be negative right there. If I was to polarize this resistor, I would say negative. That right there is positive. So it's positive, but it's pointing toward the negative source. So this is what I get about solid state. When we say the cathode, if you say the cathode has to be negative, you are wrong. It's got to be negative in respect to the anode. Right? You understand that? And it's going to be 710. So if this right here goes up to some voltage, let's say it gets up to 15 volts. Well, I'll have 15 volts right there, and over here I'll have 14.3, but they'll both be what? They'll both be positive. So the forward bias of p-n junction, the cathode has to be negative in respect to the anode, or the anode has to be positive in respect to the cathode. The anode could be negative, as long as it's 7/10 of a volt less negative than the what? Than the cathode. And we'll look at that in a minute. So what happens, this diode turns on and it lets this guy come through. So if I was looking at this with an oscilloscope, which if you hadn't used an oscilloscope, we got to use that because we need to actually see this happen. If I was looking at this with an oscilloscope, then I would see this. This peak voltage would be approximately 7/10 of a volt less than that peak voltage up there. Then it drops down, it gets below 7/10 of a volt, the diode turns off. Now what is it going to do during here? It's going to be off. Right, you understand? On the next part, so if I was looking at that output with an oscilloscope, and that's what an advantage of an oscilloscope is, a meter is going to average this out. It's going to be DC. It's DC, guys, because why is it not AC? Because the power source, the power that the diode sees is never reversing polarity. Because here's 0 volts right there, but what we're going to see is we're going to see this across the load. Now this is not good DC. In fact, we call this pulsating DC. See, I got that name. Because it pulses. Light bulbs love it. DC motors love it. They don't care if it's pulsating or not. If I put this on the stereo, it'd hate it because it buzz at me. And the stereo would constantly be turning off and on. But any resistive device don't care. Resistor wouldn't care. Resistor would work fine. All we got to figure out is what DC voltage do we have? What would we measure with our voltmeter? If this is 15 volts, if this peak right here is 15 volts, so this would be a positive 15 volts. This is the mirror image, so it would be a what? Negative 15 volts. What would my meter measure? Is it going to measure 15 volts? Huh? Can't measure 15 volts because it's 0 volts half the time. So what my meter and what my resistors are, it's going to give me an average of whatever this happens to be. It'll average it out. A light bulb, if it's in fact, a 5-volt light bulb might work off this perfect. If I put the AC on there, it'd pop, right? Because it's going to see both the negative and positive alternation. So before we can figure out these DC power supplies, we got to learn something about AC, whether you've had AC or not. If you've had AC, then you're a step ahead, and you can come up here and teach this for me. If you hadn't had AC, you need to pay a lot of attention. So the next lecture, before we get into power supplies, and these are the guys that converts the what? The AC into DC. This is the first step. In this, I guarantee you that power supply, which is over here, has diodes in it. Because anytime we go from AC to DC, we're going to use diodes. Somewhere down the line, there's diodes in this thing. In fact, this is a switching power supply. So the first thing this sees is diodes. And then they re-oscillate it, and we'll talk about it later on, the difference between these. So let's learn a little bit about AC. So this is a rectifier diode. This guy's designed, it is specifically designed to convert AC to DC. It doesn't operate at extremely high frequencies because what's the frequencies for our power? Anybody know? Here in the United States. That's 60 hertz. In Europe, it's what? Anybody know? 50. So these guys don't have to operate at extremely high frequencies. They're designed in there to give us enough current to run those. Small signal diodes are in there to switch, and we'll look at some applications for those. So the next lecture is what we call, let me run over and get something worse our voltage for it. We're going to deal with AC voltage. And of course, we know alternating current is provided by polarity constant to the law. That's correct. This repetition produces the motion waveform shown on the next slide. The AC waveform is referred to as a sine wave because its amplitude varies with the trigonometric sine of the electrical angle. Now, this is the way a sine wave, and you can see it's generated relative to the circle. See that? So if I was to come over here and stop this anytime, I'll try to stop it when it's up into a quadrant where I can draw on. Okay, it's not working for me. Oh, I know what I need to do. It stopped exactly where I didn't need it. Dang it. Then what you would see, if I drop so this is 0 volts right here. If I was to drop the vertical down, if this is 0 volts, then that actually right there would represent the voltage, right? You understand? And now this forms a triangle that we call a right triangle. And there's certain things we know, and of course, what's the total number of degrees any triangle could have? Huh? Yeah, triangle. 180. Well, since it can only have 180 degrees, we've already used up 90 of them. So the sum of them, the sum of the other two has to be equal to 92. So that means these sides have to vary in exact proportion to maintain that 90 degrees. So what we have is we have a special angle right here we call the angle theta. And this is something y'all have to know in this class. We're just going to look at basically why it's called a sine wave. And it's generated on 360 degrees. So basically we talk about electric degrees. So we say a cycle, we call this a cycle, by the way. We say it has 300 electric degrees. We call this angle 0, right? This would be what? 90. This right here would be 180. This right here would be 270. And this right here would be 360. 360 of one cycle is 0 for the next. It's just like midnight. What's midnight? It's the ending of one day and what? And the starting of the next. So these guys are constantly repeating. So 360 degrees for this cycle is 0 degrees for the next. That makes sense? So what we can do is we can come up here, if we know this angle, if we know that angle, and right now it looks like it's pretty stiff. So let's say the angle is 80 degrees. Well, what I can do is this 80 degree angle, the ratio between these sides would have to be the same, whether they're 15 foot long or whatever, as long they'd have to have the same ratio to get that what? To get that 80 degree angle. Right? Does that make sense? So I could extend them. If I extend this one, then I would extend that one. And the ratio of the two, if this stays at 80 degrees, the ratio of those sides would all have to be the same, right? You understand? So what we can do in trig is we can calculate that. And the three things we use is we use what we call the sine, and we use the cosine, and the tangent. And how I got those names, I ain't got that. Science I did. And we come up with formulas. I'm not going to tell you the way I learned it in the Navy. Oscar had a heap of apples. Sally could. Suck it that way. So we're looking at the sine. So the sine is the ratio between the opposite and the hypotenuse. By the way, this is the hypotenuse. The longest side of a right triangle is always the hypotenuse. This is called the adjacent side for obvious reasons. And then this right here is called the opposite side. Yeah, it's opposite of that. So I've got 80 degrees, and let's say this peak value is 15 degrees. Well, I could calculate what that value is there by taking the sine of the angle. So my value of V instantaneous would be equal to the sine of angle. So I'd say the sine of 80 degrees times 15. And that would give me what that voltage was at that instant in time. So the amplitude of a sine wave varies with the sine of the electrical angle. So it's called a what? Sine wave. So that's why we call it a sine wave. That makes sense? Now, y'all don't have to remember this. That's just why it's got the name, right? I think that's a pretty good animation that shows how it's generated. So this is some terms we need to understand. So these guys are constantly repeating. This guy and this guy are mirror images of each other. So if this right here is plus 15 volts, then this right here is minus 15 volts. If we flipped them and had the ability to put them on top of each other, you could not tell them apart. They are perfect. If it's a sine wave. If it's not a sine wave, then these formulas, we'll have to look at different formulas. And since it's perfect, then our meter can, if the negative and positive alternation are the same, then it makes making measuring this with a meter a lot easier. So we call each repetition of this thing, we called it a what? Cycle. The rate of the cycles is called the frequency. The time for the cycle is called the period. The period and the frequency are inversely proportional. That makes sense. The analogy I use is you're doing something. I'm putting things together, right? You understand? And I'm taking 10 seconds to put each one of them together. Right? You understand that? So if it takes me 10 seconds, right? You understand? Then that would create a frequency. Right? You understand? If I do them faster, if I do more things within a second, then that means my time per device has to do what? Go down, right? So that means if I double the frequency, the period halves. If I half the frequency, then the period doubles, right? Does that make sense? So they're inversely proportional. So frequency is rated in cycle. It's basically cycles per second, but actually we call it hertz. And we abbreviate it uppercase H, lowercase z. It was named after a physicist that was in Battle Mountain. So Alabama Power generates 60 hertz. Uppercase H, lowercase z, which actually says 60 cycles for every second. I'm having problems with it. Or per. We can use the slash for per, right? Okay. Makes sense. So if I do 60 cycles per second, and this is a cycle, so a cycle is a repetition. So every repetition, a cycle has one positive and one negative. And by the way, we call these alternations. So every cycle consists of a what? A positive alternation and a negative alternation. Are we okay? Everybody follow this up? So if I've got 60 hertz, what would the period be? So this is cycles per second. So if I've got 60 hertz, what would my period be? It would be the opposite of that, right? We would just take 1 and divide it by 60, and then this would give us the period, which is 16.666666 or 16.7 milliseconds. If I know the time, so they're inversely proportional, so what does that mean? If I can measure the period, if I take the reciprocal of that, it'll give me the frequency. If I've got the frequency and I take the reciprocal of that, it will give me the time. So time is equal to 1 over frequency, and frequency is equal to 1 over time. And we use 1 over so much, we call that the reciprocal, and our scientific calculator has a reciprocal key on it, right? You understand? So we can do this operation just by hitting that 1 key. Cycle, 1 repetition of a sine wave. Well, technically, this is for us. Basically, a cycle is 1 repetition of a repetitive waveform. So when you get into digital, we'll talk about cycles. But it won't be a sine wave. It might be a digital clock, might look something like that. But it's still going to have a frequency, and it's a repetitive waveform. Repetitive waveform, it just does what? Keeps repeating. It would be cycles too. They're consistent in sine waves. They consist of 360 electrical degrees. Each alternation of a sine wave will have 1 watt negative and 1 positive. The frequency is the rate that the sine waves occur, measured in seconds, cycles per second or hertz, and the period is the time it takes for 1 complete cycle. Everybody okay? There it is again. And then, of course, here's the formula here, BP. So we call this VP. So we have 1 positive VP and we have 1 negative VP. They are opposite and equal. We call the measurement between here and here, what do you think we call that? Now we call that V peak to peak. Are we okay? So our oscilloscope that we're going to learn how to use, this is what it measures. It measures VP. But I know if I knew VP peak if I knew V peak to peak was 30 volts, right? You understand? Then what would be peak? It was going to be 30 divided by 2, which would give us 15, right? That makes sense? Because when we calculate the DC power supply, we're going to use VP. When we measure it on the oscilloscope, our oscilloscope measures what? Peak to peak. So all you do is just measure 1/2 of it. And you can do that on oscilloscope. You don't have to measure peak. Are we okay so far? Any loss? This talks about it. This gives us different angles. It's pretty neat. This talks about how we calculate it, which I've already done, right? Opposite. Are we okay? And you're not going to have to do this. A lot of people think that if this is 90 degrees, right? And this was 20 volts. What angle would 10 volts occur at? Right. You've had AC. Most people want to, well, you're wrong. I'm sorry. You're wrong because it's not linear, right? This is not really true. So what it does is it takes off and drops down, right? You understand? So what we're doing is we're looking for an angle that has a sine of 0.5. So take the sine of 45 degrees. Y'all got y'all's calculator? Let me bring mine up. So if you got a scientific calculator, which y'all supposed to buy for the college, right? One of the things it's going to do is going to do trig. On this one, I'm going to come up here in 45, and I'm going to enter the sign for that, and it's 0.707. So at 45 degrees, it's already up to 70.7% of VP. So that means at 45 degrees, if that right there is 20 volts, that's going to be 20 times the sine of 45 degrees, which is 0.707. And we don't say 707, we say 0.707. And it's going to already be up to around 14.14 volts. So let's take the sine of 30 degrees. 30 degrees sine, and there's our 0.5 right there. So at 30 degrees, you're at half amplitude. Right? Makes sense? Now, what would be the DC average of a sine wave? 0. Why? Because the positive and negative do what? Cancel each other out. But when we start dealing with DC, we're going to get rid of one of our alternations. So if we get rid of our alternations, now the negative is not canceling that out. So that means my meter is going to measure something. It's not going to measure 50%. It can't do that because it's only, first of all, it's not going to measure peak because it's only a peak for a heartbeat, right? You understand that? It's not going to measure half wave. What's it going to measure? Well, this is what we need to know because that's what our meter is going to measure when I put it across that load in the DC power supply that's using pulsating DC. So the book says 63.7%. That's the DC average. That's not RMS. That's DC average. Yeah, let's drop back and look at that too. This is something we need to learn. If this right here is 340 volts peak to peak, would I get 340 volts worth of work? No, why? Because it's only at 340 volts for a very, very small time, right? You understand that? Of course, I get no work here, and I start getting work, then it builds up to a maximum, then automatically it starts dropping down, right? But what we need to do is understand how much work I would get into a resistor. It's not going to give me 240 volts of work, right? You understand? It's going to give me a certain amount of work, but it's going to be some type of average. But I can't use an average because if I did an average, I'd always come. So if I got a positive 1 volt right there, I've got a negative 1 volt right there. And what would they do? Cancel each other out. If I have this, so no matter what I do, so I can show y'all this on a multimeter. If I put this sucker on DC and I put it into a wall outlet, it's going to measure 0 volts because it's giving me the DC average, right? Y'all understand that? So what they did is they came up with a method where we could get, we don't call it the average voltage. If somebody's calling it, they're using it the wrong term. We call it the effective voltage. And this is the equivalent DC voltage that a resistor would see. So if I've got 120 volts worth of effective voltage, it would give me the exact same heat in a resistor that 120 volt DC would give. So what we need to do is be able to figure out how to calculate that effective voltage. So the first thing we do is they take all these values along this line, and we would say an infinite number of values, and they square them. So what happens when you square a negative number? It turns positive. Good. Then I add them together. And then I find the average of that, which we call the mean. So the mean is another name for average, if you heard that. But now we got the means of the squares. We need to find the mean. So what we do is we'll take the square root of that. And then what they'll do is that'll give us the effective voltage. And that's where we came up with the name root mean square. Root of the means of the squares. The square root of the means of the squares. All right? But we call that root mean square. Or we call it RMS. So this is what your meter measures right there. If you're measuring AC and it don't specify peak to peak, then you're measuring RMS. So when I say this has got 120 volts right there, it's 120 volts RMS. Now the problem is, to do a calculation of true RMS, it would take a computer. Y'all understand that? If it is a sine wave, if it's a sine wave, now if it's not a sine wave, this don't work. If it's a sine wave, it always comes up to be the sine of 45 degrees, 0.707. So that means I can take V peak, not just one V peak, the positive V peak, because AC has no sine, right? You understand? This sucker's switching sines every 8.3333 milliseconds. It has no polarity. So anybody says it's negative and positive, AC has no polarity because it's switching what? So fast. So I would come up here and I would say, okay, what I would do is my V average, or VRMS, all we do is take V peak, which would be equal, if it's 340 volts, what would half of that be? I would take V peak, VRMS, would be equal to V peak, 170 divided by 0.707. Oh, I'm sorry. Yes, thank you. It's tied. 70.7%. Thank you. VRMS, I just did that to make sure y'all was paying attention, would be 170. That's the instructor, or I screwed up, right? 0.707. It's 70.7%, so you have to multiply. So what does that come up and give? Yeah, 120. So if I was to measure the peak-to-peak value with an oscilloscope, so oscilloscope measures peak-to-peak, right? You understand? So we're getting 340 volts peak-to-peak right here to get 120 volts worth of work out of it.
So the 340 come out.
Yeah, that's just, and I knew 340. I knew 340 was the peak-to-peak value of 120 because I've taught the class one, right? We could have calculated it. This is what we could do. If I knew the RMS value, we can just redo the formula. So V peak to peak would be equal to V peak would be equal to VRMS over 0.707. And then if I needed peak to peak, I would just take my answer and multiply it by what. So the actual formula for V peak to peak is times 2. So all we did was rearrange the formula, right? Now, why we need to do this, of course, is my oscilloscope measures peak to peak. So if I've got an RMS value and I want to see what it would measure on my oscilloscope, this screws people up. You know, they say, well, how in the world I got 120 volts right there and I'm measuring 340 volts. Well, what they got to understand is an effective voltage, right? And what we're dealing with, it's only at 340 volts for what? Just a heartbeat, guys. It's only there. If this is 8.8, if this is 8.33 milliseconds, that sucker's up there. It's a time that we just can't understand, right? It's like driving a car and you hit the peak and you're only at the peak no time at all, right? Because as soon as you hit the peak, you're already on your way what? You're on your way down. So the time it is at peak and then it goes to zero. 60 cycles goes to zero 120 times a second. And how much current flow do we have when it's at zero? If I is equal to V over R, right? If V is equal to, if zero is on the top, we have no current at all. So what we do is we get an effective voltage. So the effective voltage it works with resistors. There's other things. When you get into AC, you're going to learn about capacitors and inductors, and those guys don't deal with this. They're totally different. But in resistors, so if I've got a purely resistive circuit, if I've got 120 volts AC sine wave, it will do exactly the same work as 120 volts DC. All your math would work out the same. You could put it across there. You throw a capacitor in there, things get interesting. We're not going to talk about those. So what happens is that instead of me doing all this math, the root of the means of the squares, if all I'm going to measure is sine waves, then my meter can just multiply it by 0.707 or divide it by 1.73. I'm sorry, 1.414, which is the reciprocal of 0.707. But the problem is, if I'm in a field where I'm dealing with waveforms that are not sine waves, then my meter's going to measure it wrong. If it uses what? 0.707. So we have meters that cost more money, and they're called true RMS meters. Those guys will give you the right value no matter what you got. Almost $400 for this guy right here. I can buy a meter, I wouldn't do it, but a Harbor Freight for $15. It measures RMS. It measures RMS because it uses 0.707, right? Or 1.414. Because it's designed to measure nothing. If you get into variable speed drives and this kind of stuff, then you're going to have to you'll need to get a true RMS meter because they don't generate pure sine waves. And they would they'll measure something, but it's not going to be what? It's not going to be accurate. So you see electricians and stuff like that, you go out there, they buy these true RMS meters, and they're wasting their money. A lot of money. But what we're going to do is I'm going to say I got 120 volts right there. If I put that sucker across a diode, how much am I going to get out? How much DC work am I going to do now? Are we okay? Now, this is only true when we're talking about DC, when we strip off the alternations. So the DC average of a single alternation, not two, right? The DC average of a single alternation is 63.7% of EP. But to me, that's just hard to keep up with numbers. So the actual formula is V peak over pi. You get exactly the same number. Take the reciprocal of pi. What do you get? 0.637. And it's generated on a circle anyway. So that's what it is. This is the true formula right here, V peak over pi. That gives me the DC average of an alternation. In fact, it's not, the DC average of an alternation is V peak over pi times 2. So I think the pi, that's right, that comes up to be 0.637, right? Okay, this is the DC average. So how much would I get out of this? I'm going to take the positive alternation, and then I'm going to clip off the negative alternation. This right here is 20 volts. What would my meter measure? Well, remember, this right here is V peak over pi, V peak over pi times 2. But I'm averaging that with what? So the formula, we call this a half-wave rectifier. And the formula is DC average. In fact, we call it volts DC because this is what your meter is going to measure. This is the work would be equal to V peak over pi for half wave. We need to. So that formula on your sheet there, on your unregulated DC power supply. DC, volts DC, HW, halfway, we peak over pi. Now you could remember the 0.637, but then you're going to have to divide that by 2 for a halfway, because we're averaging that with what? The 0. So what do we lose over there? We lose the what? Times 2. So you could use the 0.637, but for a halfway, what would you have to do with the 0.637? You have to divide it by 2. So I prefer, you can use whatever you want to do, either one of them. I prefer the V peak over pi, because that's really, because I know a circle uses pi, right? You understand? So what would be my voltage on this if I had 20 volts peak? What's that? I don't know. V peak over pi. 20 divided by 3.14. By the way, we use 3.14. You can use, no, not times 2. We lose the times 2. Yeah, we lose the times 2. Why don't we lose the times 2? Yeah, because the average is 0. Now, if I had the ability to do this, which we're going to learn, by the way, if I could take that, somehow I could take this negative alternation and make it like this, then this is going to be V peak over pi times 2. And if we call this a half wave, guess what we call this? Close. We call it a full wave. So we're going to learn with diodes. Diodes, that's what we can do with diodes. We can steer. We're going to learn how we can steer a negative alternation to a positive, or we can steer the positive to a negative. Because we have negative and positive DC power supply. A good example is how could this guy right here, if I'm using DC to control this is what we call a function generator. Now, a function generator is an electronic piece of equipment that generates waveforms. And so we have two basic categories of waveforms. I'm sorry. We have 3. We have a sine wave. We have one of these. Then we have what we call a triangle wave, which is one of these. And then there is 3. And then we have what we call a sawtooth, but a sawtooth is just a variation of a triangle wave. So a sawtooth looks like this. Now, is this DC or AC? It depends on where the 0 line is. So if that 0 line is right there, then that's going to be AC. If the 0 line down here it's going to be DC. If the 0 line is up there, it's going to be DC, right? You understand? Everybody okay? Yes, I knew there was 4. And then we have what we call a pulse waveform. Technically, it can be a square wave, but it don't have to. A square wave would mean that the time for this and the time for that would be equal. So if this was 100 milliseconds, and this right here would be 50 milliseconds, and this right here would be 50 milliseconds, and that would be a square wave. But I could come up here and have this. Right, you understand that? And then the period could still be 100 milliseconds. It's just that now this right here might be 25 milliseconds, and this over here might be 75 milliseconds. So technically, we don't call them square waves; they should be called pulse waves. But it could still be DC if the 0 reference is right there, right? Makes sense. And we'll learn about this later on. These different digital pulses that's not 50%, because we get an average DC out of this. Now, what we call this, by the way, and this is if it's like this. So let's say this is 0. So we have the period. So this would be the period, right? You understand that? But here we would do it from rising edge to rising edge, or falling edge to falling edge. Y'all understand those terms? That should make sense. The average DC And then this is going to be a percent of the period, how much it's high, like we call this a high. It's going to be a certain percentage, right? Understand? So over here, it would be high 25% of the time. And it would be low 75% of the time. Well, what determines the DC output is how much is high, not how much is low. So we have something we call the duty cycle, which is the percent of the period of a digital clock that the waveform is high. So we'd say this has a 25% duty cycle. And the average DC, guys, is just this voltage right here times the duty cycle. So if this was 10 volts, it would be 2.5 volts. So that's what I would measure on my meter if I put my meter on DC and put it across a digital clock with a 25% duty cycle. Measure 2.5 volts. So the bigger the duty cycle, the voltage goes up. The smaller the duty cycle, the voltage goes down, right? So 0 would have a 0% duty cycle. If it was up here high all the time, that would be a 100% duty cycle. And guess what we use this for? We could use it to control the intensity of a light bulb because my light bulb is going to average it out. And DC motors average it out too. So we call this pulse width modulation, guys, and this is the method we use to control DC motors. I mean, we can control them precisely just by changing the watt duty cycle. What's it called? Yeah, pulse width modulation. You can look, there's several PW. This is so popular that a lot of our programmable controllers right now comes out with the ability to generate this on one of their outputs, pulse width modulation. And you can precisely control the speed of a DC motor. In fact, variable speed AC drives use pulse width modulation to change the amplitude of the AC. But it'll use it for the positive alternation and the negative alternation. It's really neat. And then they filter it out. So half wave, we get what? Do I have a breadboard over here? Okay. Somebody give me a trainer. Bring me a resistor too. It's okay. Solid state.
Solid.
I hope so. It's pretty rugged, but if you got something in a socket in there. No, this is fine. So I've got AC right here. Let's bring the camera up. So this is a trainer. Everybody's used this trainer before, right? So we call these breadboards, and how they got that name, guys, I don't know how they got it. And this allows us to set up electronic circuits on it, right? And if we want something, these are power rails right here. So they're actually common this way, right? These are common this way. So if I want something connected together, we see people do this all the time. They put something in the same vertical line. That means that's short circuit, right? Short, right? If I want something, if I don't want it connected together, then I can put it in. I put it in a different vertical line, or I put it across this gap right here. Either one of those breaks the common between the two. Everybody okay? So here's our AC output right here. They call it generator. This is a clock. This is a digital clock. We use this in digital. This is our AC generator right here. And this is where you control the type of waveform. So there's our basic waveforms right here. We can get a sine wave, we can get a triangle wave, or we can get a pulse wave. So by flipping the switch over here. Of course, we're dealing with sine waves, right? Then what I do is I come up here and I set my frequency right here. So then I course adjust it with this knob right here. Okay? Now how am I going to measure the frequency? If we want 60 hertz. Right now we won't worry about that. We could use an oscilloscope, or we could use what they call a frequency counter. A frequency counter does that, but it's slow because it's got to do exactly what it says. It's a frequency counter. So it's got to count it, and then it's got to take the reciprocal of that, and then it displays it up on the screen. So if you ever look at a frequency counter, it's got a little LED on the left-hand side. It's called the gauge, and that's how fast it counts. So the slower it goes, the longer it's got to count, right? So when you're looking at high frequencies, the light will be on. You set the range, it'll be on almost all the time. If you set it on these low frequencies, like 60 hertz, it's going to be doing one. You got people come in and they'll be turning their knob, especially these guys. These guys have a built-in frequency counter in them. So we're going to be using this guy a lot because we're going to be generating. We're going to use transformers too, by the way. In fact, that's what we're going to use. This has got a function generator in it, but most of our labs are going to be built around what you'll be using here. So what we'll use is we'll use a transformer. And we're going to use a step-down transformer. Y'all understand that? Because we're not going to be dealing with 120 volts or whatever that is if we calculate it. We're going to go through a transformer, and then we're going to rectify that. So we're going to be using a 30-volt center tap transformer. We'll talk about that in a minute. So between the taps, we would get 15 volts. What is that? RMS or peak to peak? When I said 30-volt center tap transformer, what is that? RMS or peak to peak? RMS. Joe Blow don't know anything about peak to peak. All they know is if I take this meter and put it across there, it's going to measure 30 volts. Right? So if they don't say peak to peak, or if they don't say peak, then it's what? It's RMS, which is what your meter measures. Your meter measures RMS. Whether it's a true RMS meter, which is what this guy is, or whether it's a standard meter that uses 0.707, it's going to measure RMS. Right? You understand? This guy would measure non-sinusoidal AC waveforms, and it would give you the effective voltage. A basic meter would not measure non-sinusoidal waveforms correctly. But probably 99% of the waveforms we measure are sine waves, right? That makes sense. This wouldn't do a good job on stereo. So stereo is a bunch of sine waves, but then they're composited together. They're added together. So if you ever look at audio, you're not only looking at the bass is the main one, but then you got your trebles and your mid-range and everything between riding on the bass. I don't know if you've ever seen audio. I'll show you that. Maybe when we get to transistor amplifiers, we'll actually hook up audio to it. So we could use this function generator, but we would have to kind of figure out what the voltage is, or we can actually measure it with a watt. So let's do that. So I'm going to plug this up. And what peak voltage did we say we wanted? What peak voltage y'all? I don't know what this guy put out. I don't know why. Huh? Well, yeah, that's what we're going to calculate. We're just going to we're going to calculate what I should measure on this thing if I come up here and we have a certain peak. So you made your scope. This is a scope probe. This is a true scope probe. In AC, we don't let you use these things. These things are about $50 a piece. The little probes we let you use cost us $2.50 a piece. So if you screw up one of these, you get mad. You screw up one of those, we throw it in a garbage can and get another one, right? But what we have on this scope is we have two settings on it on the probe. And this is, we can set it as a ×1 or ×10. Now we call it ×10, but it actually divides by 10. And why they call it ×10, it's saying take the measurements that you measure and multiply it by 10 because your probe is divided by 10. That makes sense? And we do that because there's no way in the world I could measure 240 volts peak to peak with a times run probe on the scope. But I could measure it on what? ×10. Out of US Steel, we had some time 100 volts. We had a 660 volts AC out there on some of our SCR drives. And a ×10 probe, we couldn't do that because it would exceed the range of that. So we had ×100 probes, which means the probe divided it by what? 100. And why do they call it ×100? Because it said take the measurement off your scope and multiply it by what? Now these guys are computers. So what can computers do? Yeah, so what you owe this guy is you just tell it you got a time, you go into settings and say I'm using a ×10 probe, and the scope will do it for you. But if you got a regular analog scope, which I still like, this guy chops it up because it's digital. Then you would have to do what? You'd have to multiply. So I'm going to take my probe. This is ground. This is not common. So that black lead on your meter is meter common. Where can you put the black lead of the meter at? Anywhere. Anywhere inside a circuit. And all you get is you get a measurement relative to where the black lead. You cannot put this anywhere in the circuit. This is ground. So if your circuit is referenced to ground, this says ground, and I plug this up here on my plus 5 volt supply, I just shorted out my 5 volt supply. So be real careful on a scope, right? You understand that if it's ungrounded, then you can do that. But if it's a grounded circuit, which is probably 90% of the circuits are grounded, then the only place you can put this little guy is where? To the ground. And then we can come over here and take this off of DC. We don't want a parallel circuit. We want a series circuit. I'm going to take my function generator output, which is right here. I'm going to set it to a sine wave right here. I'm going to hook this up to this side. I'm going to take my ground lead and hook it up to the other side. And then I'm just going to take my scope probe and put it right there. By the way, this is really neat. You know, when you buy these scope probes, they come with these little circles. One of them's blue, one of them is yellow. And then what you do over here, where it plugs into your scope, this is yellow, this is blue. If you ever use regular scopes, you get these things crossed up all the time. So I was using channel 2. This is a 2-channel oscilloscope. And so I want the yellow lead. Now what we have on our scope, the basic controls, this is going to be upside down, guys. Let's see if I can turn back. is we have this guy right here is called volts per division. Y'all see that? Oh, look, I still want to back there. Oh. Huh? No, I've got channel 1 selected. I don't know if y'all can see that. Y'all can see the light on. I got channel 1 selected. No, it looks like halfway. So that's what halfway looks like. We don't have a rectifier or diode. It looks like somebody might have popped it. Let's make sure. Yeah, so this is I got it on 5 volts per division. I got it on my 12 volt supply, so that would be 12 volts. This is my minus 12 volts. So you can use the scope to measure DC also. It's just not as accurate as a digital meter. Then I come up here and look at my generator. I get this. I look at my clock. So my clock's working. This is your digital clock right here. You'll use this in DC. We can't change the duty cycle on this function generator. We can change the duty cycle on that one. All right, here's my generator output right here. So the generator is not working. The function generator is not working. We're not ready for Alabama Power. So y'all are going to use Alabama Power. Well, I'm sorry. I keep saying that. We're not on Alabama Power here. We're on TDM. Yeah. Well, our power is coming from the Tennessee. So let's see. Yeah. So this guy's got a built-in frequency counter on it. This is the gate. See the gate light flashing right here? I can't see it. So that's how long it's taking this thing to count. What you'll have is people come over here and they're trying to get 1,000 hertz, and they'll turn it, and then next time it updates, it's what? So you're way past it. So on these guys, what you need to do is just be patient. We're trying to get around 60 hertz. Close. That's good. And then we'll come over here and take this. This is the scope probe you'll be using in AC. Also, you can use it on your function. My thermoscope off. So this right here, anytime you select an item, it brings up a menu. So here's the menu for channel 1. You can see I've selected a watt times 1 probe. Do that. I switched it to 10. If I left it on times 1, then what I would have to do is just multiply what I measured. Still measuring nothing. I need to take it so it don't automatically go away. That's in the settings. Normally, your body works as an antenna, right? You understand that? So normally you can tell if a scope's working. You turn it down on the low voltage scale. And you just touch your probe with it. This is me. See what it's doing? Thank goodness. If we didn't pick up signals, guess what we wouldn't be able to do? So that's actually what it's using. It's using the AC that's being induced in your body from Alabama Power, and it's sensing that when you touch these. So these are called capacitive screens. The one on the HMI panel over there, since a lot of guys in industry use gloves, we can't use the capacitance of what we pick up. So that has a resistive screen on it. So it's got two membranes that's real close together, and you have to. So on those, you actually have to push them pretty hard, and that way, a guy with gloves on could do what? Yeah, work on them. So these touch screens are either going to be resistive, which means you got to put a little pressure on them, or they got to be. You can't use your fingernails, right? So those are insulators, really good. So it looks like my probe is working. So a lot of times, just to see if the probe is working, I just come up here and touch it with my finger. So guys, I don't know what's going on. I'm not good. This is not my day. This is a violet red. So what size is this? Y'all try to figure that out. What's that? Violet. .7. I was had the privilege at US Steel when I first started out there. I was a rookie, and they had a whole drawer worth of resistors, and it was just crammed in there. You know, one of my first jobs was to sort it into individual pieces. So I was doing this, and by the end I was throwing kind of like the guy on Men in Black 2. So So yeah. What I learned is in my head, I see red as a multiplier. I see it as point K. Yeah. So I was at 2.7K. Right. That makes sense. If I see an orange, I say K. If I see, that makes sense. So I see yellow, I say 100K. Right. So if I look at that, so I see red, violet, red, I say 2.7K. I don't think about the numbers anymore because I've done it so long. The numbers are there in my head. It takes a little while, guys, but that's one of the things that they really love to put on tests. Because they figure if you're an electronic repairman and you don't know the color code, then, not know it looking up in charts, but just basically know it. So it's something I need to practice. Guys, these guys are just not working. Let me go over to the other channel. But I know this channel's working. Of course, I did knock this one off the table. Huh? Yeah, it is cut. Well, according to this, neither one of these function generators will work. So the digital clock is working. Uh, yeah, somebody moved this out. So there it goes. This is working, but it's not a sine wave. It's a block. Okay, I see what it is. They had an offset added into it, which is kind of strange because usually turned all the way to the left is 0 and turned all the way to the right is maximum. This guy here is backwards. Okay, guys, what's the peak voltage? Yeah, we'll turn off this. And what we're looking for is the number of volts per division. So I have 10. So let's turn it down a notch. This shows me my 0 volt reference, so it looks like I do have some offset. So I got it on 2 volts per division. So that would be what? By the way, the way you do on this is notice here's 0. This shows me where my 0 volt reference is. And we can shift that around by using the ground reference knob right here. This is called the position knob, right? That makes sense. And what it does is it puts this little arrow here that shows me where my 0 volt reference is. Normally when we measure AC, we want that 0 volt reference to be exactly in the center, right? If I'm looking at 2 probes, then what we usually do is put one waveform up here and the other waveform by there. We just shift the 0 volt reference. Everybody okay? So we can set the amplitude right here on my function generator. So what's my peak-to-peak voltage? I got it on 2 volts per division. Or what's my peak voltage? What we're going to be concerned with here is peak. So peak to peak means I would measure all the way from here to where? All the way there. But if we center this, then what I can do is just measure one of these. Right? So what we have inside this, if it'll focus on it, is within inside each box, or they call it a gradical, by the way, we have 5 subdivisions. 1, 2, 3, 4, 5, and then we have the next unit, right? Understand? So I've got 2 volts per division, so this is pretty, when we're talking about divisions, we're not talking about the minor divisions, we're talking about the full division. So that would be 2, that would be 4, that would be 6. Now I've gotten into a little problem because now I got to figure out what those minor divisions are, right? So what do they work? Or 2, if it's 5 volts per division, right? You understand? I'm sorry, the 2 volts per division, right? You understand? Then we've got to divide that by 5, right? So what would that be? What? 0.4, right? Right? So it means each one of the minor divisions is worth 0.4. Normally what we do is we shift, this control right here allows me to shift the horizontal position. And if your peak is occurring out here in the center, it makes it hard to measure. So what we would do is we would just come over here and do what? Oh, here's the horizontal. We would just move it over till it's over onto one of these things I can measure. Right? Everybody understand that? So that would be 2, 4, 6.4, about 0.8 volts, right? Okay, so if I rectify this, what am I going to get? When I measure it with my meter. So let me get one of our diodes, one of the rectifier diodes. We'll make a positive supply first. We'll show you how to identify whether it's a positive supply or negative supply. So I'm going to come over here and so here's my diode. So what I'm going to do to get a positive supply is I'm going to turn the anode toward the source. If I wanted a negative supply, I would turn the cathode toward the source. I'm going to put this right here, right? And then I'm going to take my common and put it right there. Now I'm going to measure on this side of the diode, and you notice there's our AC. Okay. I'm going to move it over to the other side of the diode. Now we see this. Here's AC. This is coming off my function generator. There's AC. I didn't have to do that, guys. We got a 12.6 center tap transformer up there in the front. There's AC. Here's DC. Here's AC. Here's DC. My resistor is a load, so it's seeing DC. But how much does it see? So if I take my meter right here, this is the work your resistor is going to do. It's going to do whatever that average voltage is, right? So what do we think we should measure? So here's my peak voltage. What do we measure? Our peak voltage is what? 6.8. Then I'm going to divide that by pi. Y'all do that with me. What's that? 2.2. So now I'm going to come over here and I'm going to take my meter and I'm going to put it across the load. I don't know why it's jumping around there. It's measuring about 2.1. It's actually, I don't know why it's jumping like that. It looks like it's picking up some type of noise. Now, why is it probably measured a little low, right? And why? Yeah, let's look at the peak. This is on this side of the diode. This is on this side of the diode. This is on this side. Let's use two scope probes. I don't have to use another ground. 60 cycles. And I'm gonna come over here and put them on top of each other. And put them on the same voltage measurement. So the yellow is my DC, the blue is my input AC. You notice that the yellow is a little bit lower than the white. Nobody knows? Because the diode, it takes 7/10 of a volt to turn the diode on. So the diode is off until it gets up to about 7/10 of a volt. Then it turns on. So my peak output is going to be about 7/10 of a volt smaller than my input. So what we should use to calculate it is not D peak. What we should use is D peak minus 0.7. Right? So calculate that. So 16.8, so we use 6.1 instead of 6.8, right? And then it should be, our measurement should be, huh? Yeah, where you subtract 0.7, you're losing 0.7. So if I lose something, then I'm not making it a negative 0.7, it's just a 0.7. I'm going to subtract 0.7 from it. Does that make sense, Sam? The output is 7/10 of a volt less than the input because we lose the 0.7, right? So what should our output measure? Probably about 6.1, right? Almost exactly. So that's the amount of work this resistor right here is doing. It's not doing big peak. It's taking the average, which is DP. We take DP, we subtract the diode drop. For silicon, we'll subtract what? 0.7. For germanium, we would subtract 0.3. And then we use that to average, then we take that and divide it by pi to get the average output. And that's how much work that would do. If I had a 2-volt motor, it'd be running wide open. It don't care. DC motors don't care. They don't care if it's pulsating or what. It's going to average it out. This resistor does what? It averages. If I wanted to calculate the wattage that was being produced by this resistor, I would use 2.1 volts. And that's what it's going to do. That's exactly the work it's going to do. But I can't use this kind of garbage on electronic circuits because electronic circuits needs nice, smooth DC. But a lot of your analog circuits, like light bulbs and stuff like that, half-wave rectifiers are great. And we're going to see how we can smooth this out. I can smooth this out and make it almost DC. But what do y'all think we'll use? Huh? No, probably some of y'all might not know. Some of y'all have taken AC. We need something that has the ability to store a charge. Yeah, we can use capacitors, we can use inductors. Capacitors are by far the most widely used in filters because inductors cost a lot of money because they have a bunch of copper wire on it. Now, all the capacitors use a couple of plates. So we can get a really good sized capacitor that will filter this out, and we'll show y'all that in this class.
We're gonna come up and put a filter across this thing. And then once that DC pop up there, we'll see how we can figure that out. Well, first of all, we call these unfiltered, unregulated power supplies. Very cheap. One diode, a transformer to get the voltage you want. One diode, hook it up to the load. Very, very, very cheap to make these unregulated, unfiltered power supplies. Then what we'll look and see how we can steer that other. By the way, let's flip this around. By the way, I'm going to do this with power on. Y'all do this with power off. So I can get by with stuff. And now, what did I just make? I made a negative power supply. So I'll come over here and look at my signal again, and we'll turn off channel 2. And now notice the alternation is going wrong. Oops. So this would be a negative DC power supply. So all I did was just flip the diode around the other way. And the way we do, guys, all you do is see which lead is pointing toward the AC power source. So notice here I've got the cathode pointing toward the AC power source, and I get a negative supply. I turn the anode toward the AC power source, I get a positive supply. What would be the voltage? Well, if I measured it, it's going to measure about 2.1 volts, but now it's going to be what? Negative. The math don't change as far as calculating your average output. It's just that you have to identify whether you're expecting a negative or positive. Okay? Any questions so far, guys? So next class, we'll see how we do a full wave power supply, which means somehow we're going to do what? We're going to take that negative alternation and we're going to put it up top. Or if we was making a positive power supply, somehow we would take the other positive alternation and flip it down on the bottom. And then we'll get V peak over pi times 2. Everybody okay? Any questions? Y'all got all the answers? Okay, guys, that's all. Somebody had the offset so far over that it wasn't working. Are y'all dazed? Usually when I say that's it. That reminds me of a joke that I'm not going to. Well, then David joke. It's not funny. I might have heard it. What the king says is law, or whatever it is. I can clean it up a little bit. So everything the king says, they all do, because it says, the king's rule is law, the king's rule is law. And he said something about his wife, and I need to drop over.